In this video, we're going to start looking at hybridization. Specifically, hybrid orbitals. So remember our atomic orbitals, right? These are the region of space around a nucleus where our electrons are most likely to be found. And the ones that we've talked about so far, right? We can have spherical shaped regions of space, right? Those are our s orbitals. P orbitals were dumbbell shaped. Our d orbitals, they were cloverleaf or donut, right? So these were the regions of space around our atom where our electrons are most likely to be found. Hybrid orbitals are also going to be atomic orbitals. So these are still going to be regions of space around an atom, right around its nucleus, where my electrons are most likely to be found. But what we're going to do is we're going to hybridize them. So remember, a hybrid, right? Anytime we hybridize something, it's a combination. So these are going to be combinations of my typical, right, or traditional, maybe we could use that word, atomic orbitals, so S's and P's and D's, to produce new hybridized orbitals. There's still going to be regions of space around the nucleus where my electrons are most likely to be found, but instead of an S, I'm going to have some other types. So these are combinations of, let's say, traditional. I don't know if traditional is the best word. We could say of our original. Maybe that's a better way to say it. I don't want to just say atomic orbitals because hybrid orbitals are atomic orbitals. So combinations of our original atomic orbitals, right? Our S's, our P's, our D's, so on, to produce new hybridized atomic orbitals. So again, still regions of space around the nucleus where the electrons are most likely to be found. It's just instead of S, P's, D's, we're going to have different names. We're going to combine our original atomic orbitals to produce these new ones. When we combine them, we do want to remember that the number of the original orbitals that we combine is going to be equal to the number of hybrid orbitals I produce. So if I'm going to combine 2, I'm going to get 2 out. If I'm going to combine 4, I'm going to get 4 out. So the number of orbitals combined is going to be equal to the number of hybrid orbitals produced. So again, if I combine 3 things, I'm going to get 3 things out. So we're going to combine our original orbitals. We're going to produce new hybridized orbitals. The number of orbitals we combine is going to be the number of hybridized orbitals we produce. So I do want you to understand why we're doing this. So I'm going to go through a little kind of review of tetrahedral carbon. So we're going to start with carbon as my example. And if I was to look at CH4 and I was to draw the Lewis structure for it, I end up with carbon in the middle and then 4 single bonds to hydrogen. So if I was to draw my molecular geometry for this, this is my tetrahedral structure. So this here is just my Lewis structure. I'm going to erase it because we don't need it. And if I draw this, all 4 of these bonds are completely equal, right? Every single bond angle is 109.5. It doesn't matter which one you measure. They're all going to be the same. So the bond angle between here and here is the same as the bond angle between here and here, which is the same as this one, which is the same as this one, which is the same as this one around the back. So completely symmetrical. I could measure the strength of those bonds, and all of the bonds are equal in strength. So this thing is completely symmetrical. All bonds are equally strong. There are techniques where you can go and measure the strength of bonds, and they're all equal. Every single bond is exactly the same as the other bonds. So all bonds are equally strong. So if we remember valence bond theory, right? we're actually overlapping orbitals. These shared electrons are found in that overlapping region. And then if you have different types of orbitals overlapping, it's actually going to have a different strength, right? So if I was to overlap an S with an S, the strength is different than I overlap an S with a P. And that strength is different than if I overlap a P with a P. Tetrahedral carbon, right? Carbon bonded to 4 things, all the bonds are equally strong. So what that tells us is that all of the orbitals that are overlapping to give us those bonds are the same, right? If one of them had different orbitals overlapping, then the bond would have a different strength than the others. So I'm going to look at carbon's orbital filling diagram for just the valence shell, right? If I was to write out carbon, right, 1s2, 2s2, 2p4, this is my valence shell, right? My largest value for N. So if I look at my valence or my orbital filling diagram for that, I have my 2s, I have my 2p, right? If it's a p subshell, that means L is equal to 1. So I have 3 values for M sub L, 3 orientations, 3 orbitals. So I drew 3 lines. I have 2 electrons here. And then using Hund's rule, I would put 1 in each of those orbitals. So this would be my ground state, right? If I follow the off-ball principle, this is what I would get. So this is my ground state electron configuration for carbon. If I was to look at this ground state, carbon actually only would form 2 bonds, because remember when I'm forming those bonds, each is bringing an electron, right? Carbon has to bring an electron for each one of those bonds. I have hydrogens, each hydrogen, right? I have 4 of them, but they're all a 1s1. So I have 4 of those. So I would actually only form 2 bonds because one of these would overlap with one of these. And then I have another 1s for hydrogen, and it would overlap with one of those. So if I was forming bonds using the ground state electron configuration for carbon, I would only form 2 bonds. So I have 2 lone electrons. So 2 bonds would form. So this isn't right? This is if I said draw the ground state electron configuration, or using the off-ball principle, draw the orbital filling diagram, that sort of thing. This is what we would get. But this is not how we're using carbon to form 4 bonds, because I can't. So I know this is incorrect. So what I'm going to do next is I'm going to draw the excited state. And what we're doing in the excited state is I'm going to take one of my electrons and I'm going to excite it, right? I'm going to give it energy and I'm going to bump it up to the next orbital. So I'm going to take one of these S's and I'm going to move it up there. So I had 2 here, but I promoted it, right? We excited it. Remember, if we add energy, we move electrons up to the next orbital, and that's what we did. So this is my excited state. I now have 4 lone electrons, so I can form 4 bonds. So we have 4 lone electrons. So can form 4 bonds. So we're getting closer. Our problem now, though, is that one of those bonds would actually be the overlap between the 1s of hydrogen and the 2s of carbon, right? So I can have 4 bonds. One of those bonds, it doesn't really matter, I'm just putting number 1 to keep track of them, but it would be the overlap of a 2s from carbon, and let's actually do that as a subscript on carbon. So it'd be carbon's, right, 2s. I just want to keep track that it's from carbon, so I'm just going to put that as a subscript. And then it's overlapping with hydrogen's 1s. And then bonds number 2, number 3, and number 4, those would be the overlap of a 2p of carbon and a 1s of hydrogen, right? That's all hydrogen has. My other, a carbon's 2p and a hydrogen 1s. My fourth, carbon 2p, and hydrogen's 1s. So what I have is 3 bonds where I'm overlapping a p orbital with an s orbital, and I have 1 bond where I'm overlapping an s orbital with an s orbital. According to valence bond theory, one of those bonds is going to be stronger than the other 3, right? If I was to measure the strength of all 3 bonds, if this was correct, 3 of them would have the same strength, 1 of them would have a different strength. And we know for a fact that CH4 has all 4 bonds that are equally strong. So this isn't right neither. So if I was to look at the bonding of carbon, it can't be bonding from the ground state because I'd only form 2 bonds because I only have 2 electrons. If I was to look at the bonding from the excited state, okay, I can form 4 bonds because I have 4 electrons, but one of those bonds is different than the other 3, and I know that all 4 of them are the same, so I know that this isn't correct neither. So what's going on? Hybridized orbitals. So I'm going to redraw my valence shell here real quick. So I have my 2s, and I have my 2p, and there's 3 of them, and what we're going to do is we're going to combine these. So I'm going to combine, and let's just ignore the 2 because it doesn't matter what shell it's in. If I'm in my 2nd shell or my 3rd shell or my 4th shell, I can't do this in my 1st shell, right? In my 1st shell, I only have an s orbital, that's it. I can't combine it with something, right? There's no way you can hybridize a single orbital, right? You have to have combinations, and if I only have an s, I can't do that. So something like hydrogen will never be hybridized because it only has an s, right? There's nothing to combine it with. So 2nd shell, 3rd shell, and so on. It doesn't matter if I put 2s or 3s or 4s or 6s in front of those, I'm still going to combine them. If it was the 1st shell, it's only s's. Okay, so what I'm going to do is I'm going to take all of these and I'm going to combine them. Remember that the number of orbitals we combine is the number of orbitals we're going to get. So I'm combining 4, so I'm going to get 4. They're going to be degenerate, so they're going to have the same energy. And then the name of these, we get really creative. I'm being sarcastic. I'm taking 1 s orbital and I'm combining it with 3 p orbitals. So the name of this hybridized orbital is going to be sp3, right? I'm taking 1 s and 3 p's. Because I'm combining 4 things, I get 4 out. So I get sp3 hybridized orbitals. If I was to put my electrons back in it for carbon, I have 1, 2, 3, 4. So I have 4 lone electrons, I can form 4 bonds. They're all in the same orbital. So now every single bond of carbon, right, in that CH4 molecule is the overlap between carbon's sp3 orbital. It would actually be 2 sp3, but I'm not worried about the shell number, combining with hydrogen's 1 s orbital. And all 4 of them are that overlap. So I have 4 bonds that are an sp3 overlapping with a 1s. All 4 of them are the same. All 4 of them have the same strength. So when we form 4 bonds to carbon, I'm not using s orbitals. I'm not using p orbitals. I'm actually using sp3 hybridized orbitals. And it doesn't have to actually be carbon. Anytime I have 4 electron groups, and we'll make a table towards the end of the video, anytime you have 4 electron groups, it's going to be sp3 hybridized, right? Anytime I have 4 electron groups, it's a basic tetrahedral structure. And when we went through them, I didn't say, well, one bond is different than the others, right? They're all the same. So anytime you have something that has 4 electron groups, sp3 hybridized. And it doesn't matter if one's a lone pair, if 2 are lone pairs, still sp3 hybridized. Other hybridized orbitals, if I wanted 3 orbitals that are all the same, so I'm going to combine 3 things because I want to make 3 orbitals. Remember, the number that we combine is the number that we get out. So I'm going to combine these. Because I'm combining 3, I'm going to get 3. And then the name, I am taking one S and I'm taking 2 P's, so sp2. So an sp2 hybridized orbital, right? The S and the P's are my original or traditional atomic orbitals. sp2 are my combinations. One thing that's really important to know, because we're going to use this, is I do have a p orbital that's left over, right? This is unhybridized. And it doesn't just go away. So if I was to add that, right, I still have energy going up. It's actually going to be higher in energy than my sp2 orbitals. So anytime something is sp2 hybridized, I'm actually going to have 3 sp2 orbitals, right? Because I'm taking one S and 3 P's. So 1, 2, 3 things, 1, 2, 3 things. And then I do have this p orbital left over, so it doesn't go away, it's still there. So if something is sp2 hybridized, I have 3 sp2 orbitals and the p orbital also. I could combine 2 of them, right? If I need 2 equivalent bonds. So this time I'm going to take an S and a P. The number that I combine is the number that I get out. So I'm going to get 2 out because I'm combining 2. The name of it, I'm taking 1 S and 1 P, so SP. And then I do have 2 unhybridized p orbitals. So when I add those, I'm going to have 2. So if something is sp hybridized, I have 2 sp orbitals and 2 p orbitals that are unhybridized, right? I didn't have any unhybridized orbitals when I did sp3 because I combined all of them, right? I didn't leave one out. What these look like, and I'm not going to ask you to draw them, it's just that I'm going to probably draw them, and I want you to kind of understand where it's coming from. But they're literally combinations. So remember, s orbitals are spheres, p orbitals are dumbbells. So if I was to look at the shape of an sp3 orbital, it's like 3 parts dumbbell to 1 part sphere. So 3 parts dumbbell. So it still has 2 lobes, but one of them is going to be a little mismatched and it's going to be a little puffier. It's easier to kind of draw it if I draw all of them next to each other so you can kind of see the difference. If I was to draw an sp2 orbital, now it's, right, 2 parts p for every 1 part s. So it gets a little bit shorter, still 2 lobes. If I draw an sp orbital, right, it's like 50% sphere, 50% dumbbell, so it gets even shorter. So if we were to look at a typical S, right, a typical S orbital is spherical shaped. A typical p orbital, and I'm going to kind of elongate it pretty good. I didn't leave myself enough room. So dumbbell shaped, right, 3 different ways we can orient it. I still didn't leave myself enough room. The lobe should be equal for a p orbital. So the lobe I did on the top should be equal to the lobe on the bottom. They should be completely symmetrical. That's a little bit closer. So if I was to look at sp3 compared to sp2 compared to sp. So as I go from sp3 to sp2 to sp, it has more s character, right? sp3 is only 1/4 s character. sp2 is a 1/3 s character. sp is 50% s character, meaning it's 50% sphere. So it gets a little shorter and a little more mismatched as far as the lobes go. So like sp, I'm still going to draw 2 lobes. I'm going to draw that almost spherical, and then the second lobe is really kind of tiny compared to the first. This one, a little more elongated, and it's not quite as tiny compared to the other lobe. And then this one, even more elongated, and then even a little bit bigger. So it's literally a hybrid orbital, right? If you can imagine taking a sphere and a dumbbell and combining them in equal proportions, SP is what that's going to look like. So if I have 4 electron groups, it is going to be sp3 hybridized. If I have 3 electron groups, it's going to be sp2 hybridized. If I have 2 electron groups, it's going to be sp hybridized. What if I want 5 electron groups? What if I'm looking at something that's trigonal bipyramidal? I have 5 electron groups. What are we going to do? Right, when we did sp3, we already took all of my p's, right? This is 4 electron groups because I'm combining 4 things. What's going to come next? Yeah, if you're thinking D, you're right on. Right? L is equal to 2 and it's D, so M sub L has 5 values. There's 5 orbitals. If I want 5 electron groups, I'm going to take an S, I'm going to take 3 P's, and I'm going to take that 1 D. That's going to give me 5 things. So because I combined 5, I'm going to get 5 out. And then the name of it, I took 1 S, I took 3 P's, and I took 1 D. So an sp3d is going to be the name of it. I do have 4 unhybridized d orbitals. I'm not so worried that you know those. For the sp2, I do want you to know there's 1 unhybridized p orbital. For the sp, I do want you to know that there's 2 unhybridized p orbitals. For the sp3d, there are 4 unhybridized d orbitals, but we're not going to really use those. If you go on and take inorganic chemistry, you're going to use it then. But for now, you know, they are there. I'm not going to have you draw them. 6 electron groups. So I have my S, I have my 3 P's, I have my D's. I need 6 things, so I'm going to combine 6 things. I always start with the lowest. Because I combined 6 things, I get 6 out. 4, 5, 6. And then the name of it, I combined an S. I combined 3 P's and then 2 D's. So sp3d2, I get 6 of them. Again, I do have 3 unhybridized d orbitals. We're not going to really use those in this course, but they do exist. I said I would make a summary table for us, so let's do that. So we're going to have our number of electron groups, and then our hybridization. So anytime I have 2 electron groups, it's going to be sp hybridized. If I have 3 electron groups, sp2, 4 electron groups, sp3. Right, the way that you can kind of remember them is that if I was to look at the hybridization and then add up like the number of letters I have, it's going to equal the number of electron groups. So like sp, there's an S and a P, so 2 things, 2 groups. sp2, 2 P's, 1 S, that adds up to 3 electron groups. Remember, when we get to 5 electron groups, we've used up all of our p orbitals, so we have to get our d orbitals involved, and then 6 electron groups, d2. An example, we could look at ozone. We have looked at the Lewis structure for this one before. If we were to draw out the Lewis structure, I end up with this at some point going through my rules, and I would see that my central oxygen doesn't have an octet, so I would put a double bond in. When I draw my Vesper shape, right, I have 3 electron groups, so that basic trigonal planar structure, one of those positions is a lone pair, so it would be bent. But I have 3 electron groups on that central atom, right? I have a lone pair, I have a double bond, and I have a single bond. So because I have 3 electron groups, my central atom hybridization is going to be sp2, right? That's going to be the hybridization of that carbon. So 3 electron groups, sp2 hybridized. You could actually go back out to that Vesper handout that we were working with previously and then add to this if you wanted. And I would highly recommend it because then you'll have everything in one spot. If it has 2 electron groups, it's going to be hard to fit it in here, but it's going to be sp hybridized. If I have 3 sp2, it doesn't matter if they're lone pairs or bonds. If it has 3 electron groups, sp2, 4 sp3. I don't know where this is going to go. sp3d, we'll stick it over here. And then 6 electron groups, sp3d2.